Hi there, everybody. Welcome to the JVM Roundabout. Thank you all very much to TransferWise for hosting us, first of all. Obviously, if you want to get involved on the Twitter, it's at JVM Roundabout. I'll hand over to Helene to give us a quick introduction.
Hello, everyone. I'm going to start with a safety announcement first. We have two fire wardens here today, Danielle and Rebecca. And Danielle, what do we do in case of a fire?
Well, we don't panic. That's step number one. Step number two, we're here to keep you safe in the event of a fire. What that means is we'll evacuate if the fire alarm goes off. We will evacuate over that exit over there and another exit over there, which Rebecca will guide you to. You don't have to guess. You're not going to get lost like finding a lift, so it'll be fine. Yeah, you see, everybody got lost. And that's it, okay?
All right, since we got that cover, I can start. I'm Helen, and I'm a tech lead at TransferWise. I just wanted to say welcome on behalf of TransferWise and also talk a bit about what we do here. So we started our journey as an international money transfer company, and then we expanded our horizon by supporting more use cases to hold, spend, and receive money internationally. Meantime, we have built quite unique international money network that can support other people to build on top of, like other businesses or bank partners. Should I come here? Okay, video. This is the area. Sorry. So I am in small and medium business product team, and we are working on making our product easier and better for small and medium business segment of our business customers. And my team is one of the many autonomous and independent product teams in TransferWise. And we work with designers and product managers that are embedded in our teams. And we decide or prioritize which features to build for TransferWise. We also utilize more bigger clusters of teams that we call tribes. And our team is part of, unsurprisingly, Business Tribe. And tech stack wise, I think I should talk more about backend. We are pretty much a Java house. We have around, probably more now than 200 services that is hosted mostly in AWS, and we have some parts still in our Grails monoliths. And we use Kafka for messaging, and lately more and more for stream processing. And like every other company in London, we are hiring. And if you're interested in TransferWise, you can take a look at transferwise.com/jobs. There are quite a lot of jobs that are open in London and other parts in Europe, like Budapest and Tallinn. And if you're curious or have questions, you can find me or my colleagues, Daniel, Giuliano. I can see some other TransferWise people out there, Rebecca. Ask us any questions you might have about TransferWise. And that's all from me. Now I'm going to leave the stage for JVM Roundabout and enjoy the evening.
Thank you. Okay, guys. Hi, I'm Giuliano. I am one of the engineers here at TransferWise. And we have to set up things now. Wait for it. We're almost there. No, it's... Okay, it's recording already? It's recording already? Yes. Okay. Okay, so I'll talk about non-blocking database connectivity, or NDBC. And what is that? Well, that's my Twitter, that's my site, all my links are there. And I write about these things in my blog. It's quite brand new. It has like 2 posts. So if you want to join, it's the right moment. I mean, okay. So yeah, I work here at TransferWise, obviously, and we are hiring, like Helen said. So if you're interested, just talk to us. And a little bit about me. I joined the company more or less 4 to 5 months ago, and I keep talking about that I'm a open source developer, right? Because for me, it's about knowledge. Open source about knowledge, acquiring knowledge, sharing knowledge. And this year, I finished the Hacktoberfest for the second year in a row. So if you want a t-shirt, contribute to the community, it's great. And this is actually relevant because, well, let's just start from the beginning, right? Quill, I joined Quill a few years ago. Nowadays, I'm one of the maintainers. It's a Scala library that allows you to work out, let's say, a collection-like code, and that will become queries for you in compile time, right? So if you see that when it checks over there, it generates a query for you. Save, compile save. It's wonderful, it's beautiful, it's Scala. I just remember that yesterday I was defending closure in the JVM Roundabout, JVM Wars, but still. So here's the thing about Quill. We have this wonderful library to do these things for you, right? It's about generating the SQL in a safe way. And obviously later on, you execute that SQL. And to do so, we use many drivers that already exist. So we support all of those databases. Some of those databases are NoSQL, and we have some support libraries here. They don't matter that much in that case. Let's focus on the SQL libraries, right? The SQL databases. Well, like I said, we use drivers that already exist, that are already there, that were established. And this is a common JDBC code, right? You just find a connection, you build a prepared statement, and then you get the result, you iterate over it, and everything else, right? That's basic. It's well established. It works. We will just use that driver to run the SQL later on. There's just one important thing to say here, right? JDBC is blocking by definition, right? And why is that? Because if you look at the interface that defines a connection, we have statements, great statement, like you can see over there. We have prepared statements. We have the object per se every time that we execute something. So far, so good. It is what it is. That's how JDBC works, right? Fair enough. It doesn't, is that a problem? I wouldn't say it's a problem. It doesn't affect most of our applications if we are working with through the network, if you are making HTTP requests, it doesn't matter, right? You have to consider your environment, to think about what actually impacts the performance of your application. And in that case, not as much. However, some specific clients need more performance, or they need to make sure that their threads won't block when they're executing their SQL code. So we rely on Postgre Async. That's actually, I think it started as Postgre Async, but it actually has both drivers, a JDBC, an asynchronous driver from Postgres and one for MySQL. Wonderful, works very well. We used that for ages. And then that happened, right? It's a bit, okay, adding message with project not being maintained anymore. Yeah, then we started to get issues, people opening issues about, yeah, when I do that specific thing, it doesn't work anymore. There's not much we can do, but it affects directly our application, our library. We had to do something about it. And yeah, that's the issue I mentioned. Someone opened this one, drop support for Mauricio to Postgre Async because, yeah, it's not being maintained anymore. So yeah, sure, let's do it. What are our options? What can we do? And at this point, I think I was talking to Flávio Brasil. He's an engineer for Twitter, the guy that originally created Quill. And then he said something like, oh yeah, we can solve this problem. Let's build a driver ourselves. Why not, right? And that was my reaction. But interesting enough, the ones that know me know that that's not true. That's not my reaction. That's my reaction. I'm more like that, right? I see a challenge. I'm like, yeah, it sounds like a great excuse to build a database driver, right? Well, I mean, it's a perfect excuse. Suddenly, like, yeah, I'm in. Let's do it. And then that's when the whole idea started. So the first thing was, okay, we'll build a database driver. Let's have a look at what we already have. So let's see how JDBC work. And in a very, very simplified way, that's what JDBC does, right? You have, as a developer, you build a connection. I'm skipping most of that, but you guys know that's the basic of the thing, right? You build a connection, you prepare the statement, set some parameters, execute a query, It's very simple, right? I mean, who couldn't build that? It's so simple. And then I started digging to figure out how to do it. And here is my first code example. Can everybody see it? Okay, so this is very, that's just like the structured code, just to give an example of how you do that, right? Usually we don't think about it. When I'm using a database driver, what does it actually do? And at that point, I didn't know. I was like, yeah, I'm just using that. And then I was like, okay, let's do it. This is an example of how you talk to SQL Server. You can see for the port over there, 1433, it's the basic of SQL Server, right? And then you're gonna have here this wonderful bytes, this array of bytes. You use somehow some sort of input string, output string to talk to it, right? Really low level, sorry, JVM, meetup. Okay, and then you write and you send some more bytes and you read more bytes, and then you have arrays of bytes, and then you read entry pointers, pre-login packet, and if something fails, read record. Beautiful, isn't it? What does it do? Can anyone guess? Yeah, I'm trying, well, I was trying to reproduce what that previous diagram actually does, right? So this is the first example, and I was trying to reproduce that. All that code, all those beautiful bits and bytes that I had over there, they managed to get me here. Here we have 33 messages that we have to exchange with a database before your query actually gets to the database. The last line here, I don't know if everyone can see, it's a query drop table something, right? That code corresponds to the first 2 lines of the whole thing, okay? By the way, what that code actually does is something like, hi SQL Server, and then SQL Server says, hi. And that's it. That's what that code does, nothing else. It says the pre-login and everything, but the point is it doesn't do much. It just checks if it's there. When you are in that level of talking to a database, it's proper low level. You have to send bits in a specific way to say, hey, are you there? Yes, I'm here. Can I please send you a query? Yeah, maybe. Yeah, that keeps going. I'll get there. I'll get there. So yeah, 33 messages. So how do you learn about it? You read the manual, obviously. And I mean, you spend a lot of time reading the manual because you have a specific way to do so. And then you read a lot of code on GitHub. Those drivers, they are still there. Those principles, I mean, they talk to the database, right? So it kind of helps when you can dig into those drivers. The same way that I was digging into Mauricio's previous driver, because the connections are there, the bits and bytes and the order and everything. But when it comes to like SQL Server, that we didn't have the asynchronous driver, I kind of started from scratch. So I have to read I still have it, right? The manuals, and I still go through the code from the driver. And there's one interesting thing though that I realized. This is a log that I put together, right? And you can see that you have like, at the beginning you have always sent, requested, and received. That's how it works. You send the information, you request information, the database answers you back. And it feels quite reactive to me, right? Every time I send something, I get something back. Most of the time when I send something, some information, I get some information back. By the way, when you send something wrong, it's a pain because it doesn't answer back. So you don't know if it's wrong because it doesn't answer. And you don't know why it's not wrong because it doesn't say, no. It's not like, hey, can I send you a query? And that's it. It's not like, no, it's wrong. No, you cannot send me a query. You have to send me something. No, if one of those characters is wrong, you don't get anything back. It's kind of painful. And yeah, I spend my time writing these things. Okay, so now I'm reading the manual, I'm reading code. how do I define an asynchronous driver, right? Well, we have to rely on some specific frameworks. The first one is Netty. Netty is, everyone that works with Java is using Netty most likely behind the scenes. Netty, it powers like many of the servers we have, like Akka, Twitter, many things in Twitter, many things in that demand high throughput, like a strong performance when you are moving a lot of data through the servers, through the network. So that's why it's a synchronous network application framework. And besides, we have futures, Treneo futures. That's an interesting one. We have Java futures, right? That's not the best. And then we have completable features, what's slightly better. Twitter has, and then we have it like Scala features. That's better than those ones as well. And Twitter implemented their own features because there are some flaws in the previous ones. Flavio, the same guy that started Quill, he wrote his own features. He works for Twitter, so he knows what are the flaws. There's some interesting benchmark here you can check that's actually faster than all the others. It's very interesting. So we decided to build it on top of those two. And yeah, what we are thinking, we're thinking, okay, we commonly have the connection. That example is simplified, but in the real world, you don't instantiate the connection by yourself, right? You use something else, use a data source. And commonly you have a third-party data source. It's like, what's the famous one? C3PO, something like that, right? I don't remember. Yeah, that's one, isn't it? Yeah. So we consider that as well. Why should we use an external thing? Let's implement the data source as well. So we have the data source, we have the connection, we have an exchange. An exchange is a concept, it's the guy that actually is transforming the messages, right? Because the idea was, let's make it readable. Because when you're reading the manual of those databases, you have clear concepts. I'm sending a query message, I'm sending a execute action message, I'm sending a, I don't know, there's one that's the handshake message. So you abstract that, and then we have this guy that transforms the messages into the details, into the bytes that will actually go to the database. And then he's the one that talks to Netty, and Netty does that in a high scalable way. Oh yeah, and the thing is, because we are thinking about having that in a proper asynchronous way, you cannot block that. And because you cannot block that, you have to have features all the way since the beginning. Who here works with asynchronous programming on your everyday life? Who here works with web development? So all of you work with asynchronous development as well, by definition, right? All of us work with that, even though we are not manipulating that even though you cannot see you're manipulating that, it's already there. So the idea was, okay, every time that I do that, I'm gonna have like this whole the whole sequence of features, and then somehow I'll have my my result at some point, right? So if for the ones that are not very technical, I'm sorry, now you see a lot of code, okay? Okay, so here is my first example. I have the connection. This is real code. That's real code from JDBC, and that's the definition of our connection. As you can see, everything here is a feature, right? We return features of absolutely everything, including void. Did you know that void's a type in Java? It's weird, isn't it? Yeah. Doesn't sound that obvious actually, but yeah, it's there. So we have the import. So mostly when we're working with a database, we have prepared statements. We have we decide instead of a result set, we just have a list of rows, because at the end of the day, that's what it actually is, right? So we have the prepared statement as well. And as you can see, the prepared statement works with features as well. We have features, and then we have the wrapped connections that is provided by the data. Oops, I'm looking at the wrong one. This was, sorry, the prepared statement here. That doesn't matter that much. It does exactly what the other one does. It wraps the values you want to send to the database, right? And you have a row. A row returns, wraps the result of your database. Something that was important here is we wanted to make sure that it's strongly typed. what was quite difficult because we are talking about Java and the type system is kind of weak. But yeah, that one not that interesting as well. And then we have the data source. The data source is the guy that you'll be using if you are using NDBC by yourself. So you can see the methods you have here, they are pretty much the same as you have the connection, but it wraps the connection and takes care of that for you. You don't have to think about pools of connections and these sort of things. We handle that as well. So we have data source, we have Postgres data source, we have implementations of data source. The whole thing is very well modularized because the idea is, okay, it has to be simple to implement the other database drivers, and every time you decide to use one of them, you don't have to take like everything, right? It should be light. You shouldn't have anything that you don't need. There's a moment when you have to start the whole thing, right? Because thinking about futures, there's a moment when you have to eventually unwrap that. You have to say, okay, I want that result at that point. And that's where you should do that at the end of the world, right? Or at the edge of your application. Sometimes you don't even see when it happens. If you're working with Spring, for instance, the ones that were there know what I'm talking about. Spring unwraps that for you at the end of the day, but you don't see it. But you can just execute that and say, okay, I want that result in 1 second. 1 second is way too much. In that amount of time. Otherwise, that will give you a timeout exception. So I have the pool data source. You don't have to worry about that one as well. It's already wrapped as implementation of the previous data source. It gets complicated in the data source supplier. Because to build a lib that's entirely asynchronous, you cannot block absolutely anything. If some of the libraries you have over there, sometimes they wrap the result with a future, but at the end of the day, that's not asynchronous because behind the future is still being blocked. You need something that's intrinsically asynchronous to produce your result, and you cannot block at any moment in time. That's why this code doesn't look like Java code at the end of the day, right? I mean, some of my peers complain that I write code that doesn't look like Java, but like it's my thing, right? Like I work with Clojure, and then let's push it a bit more. Let's make it a bit more functional. It's doable. It's painful. It's doable. So we have those guys here. We have many objects that are related to marshallers, and unmarshallers are the guys that they try to interpret the results and the messages you are saying to the database. We have many abstractions. When you are reading the code from the previous drivers, it is very procedural, and it's difficult to make sense out of it. The idea here was, okay, let's abstract the messages. Let's make it a lot more composable. So even this is the data source supplier, meaning that even the data source, you don't use the data source at that very moment, use something that you generate a data source for you. So the whole process works in the sense of you have a data source that will provide you with the future of a connection, that when you try to execute something, provide you with the future of a result set, a list of rows, that will provide you with the future of something else. So it's entirely declarative. That's the idea with something that's entirely asynchronous. And here we have the net-e4 thing. This is the specific thing of net-e4. I think that's what caught my attention. You don't write that on your everyday job, right? You don't have to go so into the details. And like it fascinates me that when I can go so deep down in something that commonly we don't do. It's way harder, but like, yeah, I enjoy it a lot. So here we are generating the threads, and see, it's beautiful. It's art, isn't it? I mean, it's not Clojure, it's not Scala, but it's beautiful. And then we have to create, like I mentioned, we have to create a connection. We have the create connection supplier that supplies something, that creates something, that creates something. But the thing is, you just declare that. When you start executing that at the end of the world, we have a future, and then you decide what you do with that. This is one of the examples I have. So that's how you use it. So you have a data source here, and then you say query that, and the get timeout is the one that defines how long your code has to actually execute that to bring you a result. Otherwise, timeout. Like futures work, right? So okay, we have the data source test. Doesn't matter anymore. More code, yay! So Oh yeah, I talked about those guys. We have, as you can see here, we have many of the concepts that we use on the everyday development to some extent. Functions, we have by functions, you have suppliers, you have schedulers, and all that beautiful things that you have when you are working with the Java concurrent package. The next one would be a channel. And this one is an interesting one. That's the one that defines how you talk to the server, saying that, okay, you can send a marshaller in this, you send a message with the one that interprets the message, you receive back a message with someone that will interpret the message as well, right? It is done via net channel, where Java can be difficult, right? Well, where you have your context, and as you can see here, this is the guy that requests something, that built that message, request tells the server, please send me back something. This is a hi, send me hi back. And here we have the other ones as well. Receive, when something, oh, this is the timeout one. When receive is still pending. We have other messages, channels closed. This one doesn't matter that much. It's way into the detail of the thing. Okay, we have the channels, we have the marshallers, I talked about that as well. We have here some of the messages I mentioned, the way that they are encoded and decoded with like sync, startup, SSL, and it keeps going. We have the exchange, that's one of the marshallers. So yeah, read the manual, it will make sense if you read the manual. But then again, maybe. But the idea is, this is a message that represents a query in Postgres. If you have a look at the MySQL implementation, is entirely different. We have the exchange here, the guy that actually worked out those queries, those messages, the one that you send a message, get it back, and keep the machine running. Because it's always a long sequence, like the other one I showed you. You send a query, you actually exchange 33 messages, actually more. We have the exchangers, simple query exchange. I think it's enough code. You suffered enough already, right? So, okay, you have a database driver, right? Now what? No one writes code with a database driver by yourself, right? Nowadays, you always use that with a framework or something like that. Remember at the beginning of the talk, we started the whole thing because of Quill. So recently, what happened was that I finally managed to integrate with NDBC with Quill. So now it's actually one of the drivers behind that tool. What generated like a nice tweet from what would be the leader, the technical leader of Quill nowadays, a guy, Alexiov, that works for NASDAQ, I think. And he was a speaker in Scala Days or Scala B or one of these Scala interesting names recently. He's a guy that has like a great knowledge about it, and it's really cool to work with him. By the way, when you join the open source community, you always eventually will like have the opportunity to work with like these great people. You learn a lot. I strongly recommend that. So in summary, it's written in Java because of adoption. The main idea was, okay, the previous one was Scala, right? But now that you are writing that, what about we build that in Java that will be easy for Kotlin to adopt that, or Clojure or Scala. So that's personally speaking, I think that something that should be that well spread around to make it easy to be adopted should be written in Java, because it's really, really low level and you don't suffer with annotations. Netty for asynchronous communication, well established. Most of the powerful tools we have that deals with I/O is powered by Netty, great tool, and Traneo futures for high performance. The future. So plans for the future. Data streaming, I didn't talk about that, but we actually can stream some of the data. It's like a work in progress. We're using that reactive project reactor. That's it, right? We have like our implementation. What's funny, and remember I mentioned the type system in Java is weak. You cannot transform anything to anything. So it's painful. You have to implement your maps and flat maps yourself. I mean, it's hard work, but well, it's for the greater good, I think. I intend to write the SQL Server driver. I intend to write a Clojure wrapper. As promised, I promised someone that I would mention Clojure here. it's powered by NetE4, but possibly we could have Akka powering that one as well. It would be interesting because Akka is quite powerful. And if you have Akka already in your stack, maybe it's easier to adopt a tool that uses Akka. And this one is interesting, isn't it? Thinking about adoption again, if you want to make something well-known, you kind of have to have, I don't know, a deal with the devil sometimes. And then the challenge here is the fact that Spring is based on JDBC, like most of absolutely everything that talks to the database, meaning that's not reusable. I cannot just implement that. I have to rewrite absolutely everything that uses JDBC, what makes it quite hard. But hey, I'm up for a challenge, right? With the devil. That's it. Questions? Wait a second. Can someone please? Thank you.
Hi, just one question. The train.io, do they have an IO implementation as well, or just future? And
What, sorry?
do the library, do they train? Do they only provide future, or they have IO as well?
Just futures, promises.
So there's no IO. Okay, so that
No IO.
answers my question.
That's why we're using NetE. Yeah.
Hi there. Congratulations on having your pull request merged in GitHub. This is always, a pleasant thing to happen in anyone's life.
It's my project as well.
Yeah, certainly. Now, I'm not necessarily coming from the Java backend development, right? So I was just wondering, like, when it went down to picking the actual reactive programming primitives, you went for the futures, aka promises. Why not reactive X or something more complicated then?
So that's why we started before it became a big trend. Like, I mean, let's just start simple, right? I need those basics first before I have something streaming data. So the reactive one is kind of a work in progress, but it's like a lot more complex to implement that yourself. So it's a work in progress. And because we started, they started like a while ago, and we work on that one in our free time, right? So we defined first how we could replace the basics of database drivers. Streaming would be the next one. And we started on top of Trineo because we had that one available as well. That was the idea.
All right, thank you.
Thank you. I think there's another, yeah.
Hey, so the objective of this this project was to create asynchronous calls for databases, right?
Yeah.
So couldn't you just wrap the database calls in the asynchronous Java primitives?
If you do that, it's not exactly asynchronous, is it? It's still being blocked because when you connect to the database, opening a socket by yourself, like the drivers do, every time that you do anything, you are actually waiting. So the future would be waiting. It fires up, but it can take a lot longer. So the idea was, let's make it entirely asynchronous. If you want to do something, do it right. The concept is there, so let's work hard to make sure that you follow the concept from end to end. That was the idea. You can still wrap that up, and sometimes it's kind of a solution, sometimes it's enough, but we aimed for the hardest possibility.
So it's a difference in performance. So I guess you get a little bit more performance,
yeah.
But it's not going to be like massive. It's going to be like marginal.
It depends on your perspective, right? I mean,
for latency.
If you have like Kafka in the middle of your service, it's nothing. But for, let's say, Twitter, it makes the difference.
Okay.
All right. I get that. It's not like for everyday job doesn't make a massive difference of your everyday life. Yeah. But
it's for low latency, basically.
Yeah, exactly.
Okay.
I mean, for like the hardest situation it could be. And then again, I enjoy the challenge. So that's the idea. Yes.
Does it benchmark? Have you seen a noticeable improvement, or
in Trineo, just Trineo has a benchmark. If you go to the site, you can see the benchmark compared to all the other features. And DBC, not yet. Would have to test it as well.
Okay, cool. Yeah.
I spend like a time like you guys have no idea how difficult it can be to isolate transactions. Like it was a pain because I managed to get this pull request merged months ago. And then there was one test failing. This one test was about a transaction that would fail intermittently. I had like a sequence of futures. You transform the sequence of features in a future of a sequence. So I executed all together. But if you want fail, I have to roll back everything. and once in a while it wouldn't roll back everything. It took me a long time to figure why that happened. So yeah. Do you have any more questions? Oh, sorry, I forgot about it. We have T-shirts for the ones asking questions. So one, no, the guys that asked you two, three. Sorry, three, just three. now you have to ask me a question. If you don't ask me a question, I will ask you a question. That will be way harder. Can you give him the mic?
You don't get another T-shirt there.
Yeah, that's not like, thank you for setting up. But anyway, like I was wondering, like in this particular implementation of the futures, through the flow of a single request, single response pair, like in a proper like server application, how many thread transfers actually happen through this? Because you would expect, like in JavaScript, any consequent promise actually, you know, breaks the synchronous context. Everything gets enqueued into the next frame inside the event loop. Do the threads actually change a lot when you do these kind of, you know, consequent operations and working with the database driver using promises? Or are they, you know, like they do not actually change anything? They just make the programming asynchronous, but not necessarily happening in the other thread.
They make it that asynchronous, but at the end of the day, we still have to do, every exchange happens in a specific order. So you have to make sure that it keeps that order. I cannot just like, let's say, split the 33 messages and fire them up all at the same time. I need that specific order. So we don't, oh, that's a proper hard question. But no, we have to keep the order, therefore, we cannot like split more
yeah, it's supposed to be this way actually.
Yeah.
And pretty much that's how it is. It's like they're supposed to, you know, it starts in some context and it's actually retains the actual, you know, sequence of the events and not doing things in parallel, obviously. But yeah, thank you very much.
Thank you. Sorry, I think I'll have to give you like your T-shirt to him after this question. It was a hard one. We have another one.
Everyone's going to hate me for this question, but why Java and not Python, which would be a hell of a lot easier?
If I write that in Python, who else could use it?
Me.
No. Which other environments could use it?
You could make so you can make an API call. You could actually make the database an API call, or did I get it wrong?
No, sorry, that's not my question. Is we built, the point is we built in Java for distribution.
Right.
I could build that in Python, but what's the other environment that could use that? Because if I build it in Java, I could use that in Java, Scala, Clojure, Kotlin, Cylon, and keeps going. Even Python can use that.
Exactly.
Right. That's the main reason. Besides, my background is in the JVM mostly, and I knew we had Trenail that Flavio built, and we had Netty. So besides, I'm sorry, Python is really slow. It is the Ruby is slow as well. You don't have to feel bad. Okay. Thank you very much.
All right, thanks a lot, Giuliano. We'll take like a quick couple of minute break. If you want to grab some pizza, another beer, get a loo, and then we've got Derek. You're up next, yeah? Okay, brilliant. Our second talk tonight is from Derek from ThousandEyes. So yeah, hand you over, Derek.
Hello. Just gonna wait for the presentation to show up. Play some elevator music. There we go. All right. Cool. Is it gonna come up on yours? All right. Sweet. Cool. Hi everyone. Welcome to Not a Chat App. My name is Derek. I'm a software engineer at ThousandEyes, and today I'm going to talk to you about how we use WebSockets to make our systems fully reactive. So full disclosure, it's my first time doing a meetup, so I'm a little bit nervous. That's why I have the flashcards, because I'm old school. But yeah, please go easy on me. So I wanted to talk about this topic because I feel like a lot of the things we see on the internet today about WebSockets and like reactive programming generally cover use cases like consuming stuff from a Twitter feed or like chat applications. And it's obviously not the type of use cases that our companies or our businesses are in. And they don't necessarily address things that you see in real life systems and real world engineering problems. So my goal for the next 30 minutes is to give you an overview of what being reactive means for us, show you some code for what reactive programming looks like at ThousandEyes, and give you an overview of like the lessons that we've learned along the way. Cool. But before we go any further, I want to first define what reactive programming means in the context of this presentation, because I feel like there are a lot of definitions out there. The term is a little bit conflated. The term is a little bit conflated, but for the context of this presentation, I'm going to say reactive programming is programming with asynchronous data streams. So this is, like in the talk previously, the asynchronous data stream could be the bytes coming out of a database. It could be clickstream. It could be user input, so someone typing into a keyboard. For us, it's the events on a message queue, but asynchronous data streams can be anything. And I think this concept will be a little bit clearer when I show you some code. So for today, I first want to give you a quick overview of ThousandEyes and the specific team that I work in. Then I'm going to take you through our architecture, show you some code, and finally some lessons learned going through all of this. Now, ThousandEyes is a software as a service company. Our main aim is to help our customers gain visibility into the internet. And our customers are mainly enterprises, and I'll kind of go into a little bit more detail about what this means later. But within ThousandEyes, there are multiple product teams, and I sit within one of these product teams. And our product team is called the Endpoint Agent. The Endpoint Agent is a piece of software that our customers can install on their computers or on their employees' laptops to gain a better understanding of their employees' experience with the internet applications that their employees use. So to give an example, if you're a company that's using Jira and you're using the cloud-hosted version of Jira, then our software can help you figure out if your employees have issues connecting to Jira. It'll give you metrics to diagnose the problems. So concretely, the Endpoint Agent is a C++ piece of software that we install into the employee's laptop. It gathers data and various metrics, which it then sends to our backend. And then we also have a web application that kind of makes this stuff pretty and shows it on graphs and stuff. Now, to kind of explain how reactive programming is involved, I want to explain a feature that our product supports, which we call scheduled tests. And scheduled tests effectively allow our customers to answer the question like, what is the experience of GitHub.com for my employees in the London office? So pretty vague, but we can kind of dive into what this means. So from our point of view, we require two pieces of information from our customer. Firstly is a URL for the application that they're interested in monitoring, in this case, GitHub.com. And secondly, the agents that are applicable for this test, in which case, the agents in the London office. This is configured in our platform through a web interface. And when this is done, our endpoint agents will begin collecting various metrics. So for example, the endpoint agent will send an HTTP request to github.com to kind of measure high-level response times and status codes and that kind of thing. Or it'll perform a path trace to figure out how the data moves through the internet. And it collects all this data and it sends it to our backend, and it allows us to draw pretty graphs and charts that look like this. So for example, on the top half of the screen, it's a timeline of the latency to github.com. And so what the agents are actually doing is it's poking github.com like every 5 minutes, and we're able to plot this timeline of the latency and how it changes over time. At the bottom of the screen, there's a path trace. So it's how my agent's request is going to github.com and all the intermediate nodes in the internet that it goes through before it hits the load balancer at the end. So this is the kind of like data and the world that we're working with. But to summarize, scheduled tests work in the following way. Firstly, we configure a test on the web interface. And secondly, the endpoint agents run the test and collect the metrics. Now, from a backend point of view, aside from like persisting the configuration of the test, and collecting the metrics from the endpoint agent. Most of the work on the back end becomes figuring out which agents need to run which tests. And this is where kind of the reactive programming stuff comes in. So let's take a look at how we're able to do this. I first want to explain some of the interactions between the endpoint agent and the backend. And one of the most important things that the endpoint agent needs to do is check in with the backend. And what this means is that the endpoint agent will periodically poke an endpoint in the backend and say, hey, I'm currently connected to the TransferWise network, or my current location is in London. And you can kind of think of this like a heartbeat. It's effectively the agent submitting its most recent state to our backend. And it's also what allows us to filter out these agents later. So recall on the slide previously, we want to target all the agents in London. And this is how we're able to begin targeting that, because the agent will submit its location. Now, from a backend point of view, this is what happens when a check-in happens. We first put the payload into an asynchronous event queue. We then have a microservice, which we call the scheduler, which listens to this asynchronous event queue. It figures out which tests this agent actually needs to run, and then stores this as state somewhere. And then finally, the agent polls the scheduler every 10 minutes for the test that it needs to run. So every 10 minutes, it pokes the scheduler, hey, what do I need to run? And the scheduler gives him the answer. So that's how it works at the moment. Now, we use Kafka as our implementation of the asynchronous event queue. And specifically in the Kafka ecosystem, there's a library called Kafka Streams, which allows us to do effectively reactive programming on the data in a Kafka topic. And a topic is basically like a channel where the message is published. So for example, in our case, we have a topic called check-ins, or if you're an e-commerce app, you might have a topic called orders or payments. But effectively, Kafka Streams is a library that lets us do reactive programming within our applications. So let's look at some of the code and see how this looks like inside the scheduler. So I'm a little bit nervous to show Kafka Streams code because we have TransferWise people, and apparently you guys use Kafka Streams as well. So if I get anything wrong, don't shout at me. So what we want to do first is start off with the Streams builder, which is effectively our entry point into the Kafka Streams library. It allows you to set up like various pieces of configuration, but for the purposes of this, just think of it as like the entry point. And what we want to do is start off with the stream method. This returns an object called a K-stream, and it basically tells the application to start listening to the Kafka topic called check-ins. The API of the K-stream object that is exposed is very similar to like the RxJava observable, or like the Flux reactor, or even like the Java 8 stream for that matter. So it's, yeah, like kind of generic stream processing API that you get to use. So it has stuff like map, group by, reduce, etc. But what we want to do first is perform a left join with the tests that our customers have configured. So the way a left join works is you can kind of think of it like a database left join. You first supply effectively the foreign table, in which case it's this test configurations global table bit. The second thing you want to supply is the foreign key, in which case it's the customer ID on the check-in. And finally, we output the result of the join, in which case we just want to do a pair of the the check-in and the test configurations. The interesting part here is this part, the test configurations. Effectively, the test configurations is also an event or a topic on Kafka. And what this global table method does is it pulls all the data from that topic and keeps a local cache within the service itself. And this is what allows us to do this left join. The cache itself is keyed on the customer ID, which is the same foreign key that we're joining on. And so that's how we're able to like join the two pieces of information together. If you've looked at stuff like RxJava or like Reactor before, and you're familiar with like marble diagrams, this is the one for the join operator. If this is like intuitive to you, I'm very jealous, but yeah, here you go. But going back to the code, the output is a pair where the first value is a check-in and the second value is a list of test configurations. After that, we want to do a map operator, and map is basically the same as any other map operator that you've seen in any other programming languages. It takes an input value and it turns it into an output value. And in our case, we call this assign method on the results. And what the assign method does is it looks at the tests that are in this customer's account, applies the filters to the check-in and see which ones match, and then output the list of tests that match this check-in. Finally, for each test that this agent needs to run, we save it, and then we also publish it to Kafka. And so because we've saved it as state, when the agent pulls the scheduler for, what test do I need to run every 10 minutes, the scheduler has the answer already. Now, like a natural question to ask is like, why are we publishing like the set of assigned tests to Kafka as well? Well, it's because we want to be able to react on this event later. Because it's still not very good that the agent needs to pull the scheduler every 10 minutes to be able to get the latest tests. For a few things, like it's definitely very bad user experience, because when a customer defines a new test in our platform, they have to wait at least 10 minutes before the metrics start coming in. And that's one, that's confusing, and two, that's just not a very good user experience. So we want to get to a state where the agent doesn't actually need to do this 10-minute polling. And this is where we kind of introduce WebSockets to help solve this, right? So just a super brief introduction into what WebSockets are. It's basically a communication protocol that allows two-way communication between a client and a server. So it allows client to send messages to server, and allows the server to send messages, push messages to the client as well. You kind of compare this with the traditional HTTP approach. Only the client is allowed to send a message to the server, and the server has to reply based on a request from the client. So kind of how does this work for us, right? So the obvious use case is for our backend to proactively push messages along the WebSocket connection to the agent when it sees that it needs to assign a new test. So, at the first round, my agent might just have a test to github.com, and then a user might configure a test to Google Mail, in which case the backend should just push that along the WebSocket connection without requiring the agent to pull our backend again. So how do we actually make this work? Currently, the scheduling only happens when an agent checks in with our backend. So the scheduler only runs as a result of a check-in. It doesn't run as a result of anything else. And the scheduler doesn't know when the test configuration changes. But the test configuration changes are already events on Kafka, right? So this is what allowed us to do the whole left join thing we saw a couple slides back. So then we're able to listen to these set of test configuration changes as well, since it's already on Kafka. So we introduced another service to react to test configuration changes, which we've called the reconciler. And the name will be a little bit clearer later on. But of course, no surprises, the reconciler is also implemented in Kafka streams. What it does here is first, it listens to the stream of check-ins. So same as before, we start with this builder, and then we call stream, and the application begins listening to this event on Kafka. We filter based on time, because we only care about check-ins that are effectively active. If an agent hasn't contacted the backend within the last hour, we basically don't care about scheduling tasks on them, because they're probably offline if they haven't contacted us in the last hour. So we filter these out. And again, the filter operator here, very similar to filter operators you've seen in other places, like in the Java stream, or or like JavaScript arrays. What we want to do next is we group them by the customer's account identifier. And so this allows us to process the set of check-ins that are specific for a given customer. And finally, we perform an aggregation over this list of check-ins. And what aggregate does is it's kind of similar to like methods like reduce and collect. It like takes your stream of stuff and applies some kind of meaningful combination to it and outputs the result of that combination. So in Kafka streams specifically, the aggregate operator takes 3 arguments. The first one is a lambda that sets up your aggregation container. In this case, it's just a list for us. The next argument is also a lambda that defines how you merge each event into the aggregation container. So for example, in this case, we're just adding the check-in into the list, and then we're just returning the list itself. The good thing about Kafka streams is that the result of this aggregation is accessible in a subsequent step. So it effectively like stores the result of this aggregation as a cache on your service. And this is what the last kind of parameter is for. You basically give to Kafka streams an identifier for this cache so that you can access it at a later step. And this will become like clearer later. So as you can see, like the aggregate method is very similar to like stuff like reduce and collect. The next thing the reconciler needs to do is actually listen to the stream of test configurations, because ultimately that's what we want to react on, right? So again, we have another kind of stream where this time, instead of listening to the check-ins, we listen to the test configurations. We do another join, and here is where the cache from before is relevant, because we created a cache called active check-ins. We can access it again in the join. This time, we're again joining on the customer's account ID, because the cache is keyed on the customer's identifier. And finally, we just output the stuff that was in the cache that we found. So this returns a stream of a list. And so we flat map over that. And what flat map does is, if you have a stream of a list of stuff, then it just flattens it out to give you a stream of stuff. It's one of those operators that's like a bit hard to get your head around at first, but it's effectively identical to the Java 8.1 and all the other ones that are out there. Once you get your head around it, it's actually pretty simple. And finally, once we have the individual check-ins themselves, we just play it back to the same Kafka topic that the scheduler is listening to. So then how has this actually affected our architecture as a whole, right? We have the scheduler, which is still listening to check-ins, and it's returning test assignments for each check-in. But now we also have the reconciler that listens to test configuration changes. It keeps a cache of the active check-ins, and when a test configuration change occurs, it replays this information back to the scheduler. So that means whenever a test configuration has changed, the scheduler knows about it immediately because it's listening to the check-ins and we're replaying those check-ins. This also means that our backend is now able to schedule tests for agents when a test has been modified, and it doesn't require the agent to poll the backend anymore. But that's not enough, right? We still need to have a mechanism of pushing these messages to the agent itself. And so for that, we introduce 2 more microservices. We have a component called the publisher and the WebSocket server itself. The publisher is pretty simple. I'm going to go through this really quickly. It's another Kafka Streams application, surprise, surprise. This time, it's listening to the test assignments, which, if you recall, is the output of the scheduler. It then enriches it with some metadata. And then for each enriched test, it pushes it to a Redis topic. Now, Redis topics are kind of different from Kafka topics in that they're fire and forget. So if no one is listening to a Redis topic, the message just disappears. But the good thing about that is they're super lightweight and pretty easy to scale and manage. And then we have the WebSocket server. Now, the obvious thing that it needs to do is manage the WebSocket connection with our agents. Now, the WebSocket spec doesn't actually define any sort of application level protocol between your client and the server. All it cares about is this is how you set up a pipe, this is how you set up the connection, and what you send along the pipe is kind of irrelevant to the WebSocket spec. But so it's usually a good idea to define an application level protocol for the stuff that you're allowed to send and receive along the WebSocket connection. And so for this, we use Stomp. Maybe some of you guys have heard of Stomp, but it's just a protocol that defines what the WebSocket connection, what messages are allowed to go through the WebSocket connection. It's a protocol that's been around for a while now. It's pretty simple to understand, and it kind of just works. So that's why we chose it. The idea with Stomp is that each client tells the server what kinds of messages it wants to listen on or what kind of messages it wants to subscribe to. And then the server sends the relevant messages to the client based on their subscription. So in our case, we have our own WebSocket server, and the client is obviously the agent that's living on the employee's laptop. So what we do first is we open the WebSocket connection and the connection established. And then the agent says, hey, I want to subscribe to the test assignments that are relevant to me. And the WebSocket server says, hey, good job, you're subscribed. When this happens, the WebSocket server will subscribe to Redis. And the topic on Redis is specific to the given agent themselves. So only the agent's test assignments are coming out of this Redis topic. When the publisher pushes an assignment on this Redis topic, the WebSocket server hears about it. And finally, it forwards this message along to the endpoint agent. So this is kind of our architecture with the WebSocket server. But if we put this all together, this is how it kind of looks like. We still have the scheduler, which is listening to check-ins, and it publishes test assignments back to Kafka. We have the reconciler, which keeps a cache of the active check-ins. And when it hears about a test configuration change, it publishes these active check-ins back to Kafka again so that the scheduler can listen to it. And once the scheduler sees some check-ins, it will generate new test assignments that are relevant for this agent. We have the publisher, which is listening to the test assignments topic, which is the result of the scheduler, and enriches it with some metadata, and then it pushes it to Redis. Finally, we have the WebSocket server that's listening to the Redis topic, and it forwards this message along to the endpoint agent. So that was like a super intense session of like how we've managed to schedule all this stuff. What impact has it actually made, right? This is a couple months of engineering work, and if we have nothing to show for it, it's kind of not very good. Now, when using the polling approach, it would take at least 10 minutes for a new configuration to be published to the agent, because that's just how the polling interval, right? But with this WebSocket approach, we managed to minimize the time it takes for a test assignment to reach the agent from 10 minutes to 10 seconds, because we push it to the agent immediately once it's there. So that's a great improvement. But of course, this also means a much better user experience, because now when a customer configures a new test in our web application, they see the results pretty much immediately or within like a couple minutes. And that's a great thing for us. It's a lot less confusing for the user, and it's just overall better. It opens the doors for a lot of new features as well. In the next couple of months, we're gonna add like a run now button to a test. And effectively what we want that to do is push the test configuration to the agent immediately so the agent can start collecting metrics straight away. And effectively the goal is to kind of have metrics show up within like a minute or less than that. And this is good for us because it addresses like an ad hoc troubleshooting use case that a lot of our customers have. And so not only is like it's a performance improvement, but it also kind of lets us implement new and better customer features. And for this, we plan to leverage a lot of the existing components that we've already built. But of course, not everything is easy and not everything is rosy. Building a reactive system is difficult, and it's super easy to like introduce bugs. In traditional systems where your data is stored in a database, if you have a bug, it's usually pretty easy to just like look into your database and figure out what's wrong. Like if the row has the wrong value, then you can usually pinpoint where your bug is. But in an event-driven system, you don't really have like a database. It's quite hard to look inside your event log and try and see where the problem was. So bugs are pretty hard to solve. And the way we've kind of addressed that is just through good monitoring and good operational excellence in general. Through our monitoring, we've kind of actually uncovered a lot of issues that we didn't initially realize. And another thing for this kind of like reactive architecture to work, having like a push-based mechanism in the middle usually is the last piece of the puzzle. So for us, the push-based mechanism is the WebSocket server, but that was almost the easiest part of this whole thing. The harder part was more to model everything as an event, so that eventually when the WebSocket server does get introduced, it has that event already and it's able to push it along. So modeling everything as an event, you kind of have to flip your way about how you think about problems, and it sometimes makes simple problems pretty difficult to solve. Of course, if everything is asynchronous, then timing also matters. We kind of had a few weird issues where caches were being populated in a downstream or in an upstream service, but the thing downstream wasn't warming up its cache quickly enough. So when a message got pushed through, the right thing didn't happen because the cache on the downstream server wasn't like warm, and so it didn't produce the right result. So again, kind of like with asynchronous systems in general, timing is a big factor. And for us, again, it was down to monitoring and good operational excellence that like allowed us to figure out what the problems were. And finally, writing a WebSocket server in Java is not that straightforward. A lot of the things you see online is about writing chat applications, which we're obviously not. And like a lot of the literature out there doesn't really help. It kind of usually talks about writing single instance applications where for us, we want to run multiple replicas. And so like a lot of the frameworks that are there as well don't really help. A lot of the time we had to kind of dive into the framework code and look at the libraries and debug the libraries themselves to actually figure things out. But kind of these were the key takeaways for us. Ultimately, it was a great engineering challenge to solve. And I really think that by embracing a reactive architecture, we brought a lot of value to our customers. Now, before I conclude, I just want to say thanks to TransferWise and JVM Roundabout for having me. I'll be hanging around later as well, so if you have questions or you want to chat, feel free to come along. But otherwise, I hope tonight I've given you a good overview of how we run our systems, the types of challenges that reactive programming brings, and some inspiration for how to make your systems more reactive and event-driven. Thanks. Yeah, if you want to do questions here as well, that's cool. Yeah.
Cheers, couple. First, why did you introduce Redis pub sub in the middle rather than for the publisher, rather than connecting
listening to
directly
Kafka straight away?
Kafka?
Yeah. So it's kind of going into the weeds of how Kafka actually works. So the way Kafka sends messages to your listeners, it's based on like a partition key. So effectively, each message has a key. And that key lives on a particular partition on a node on Kafka. And when you have subscribers listening to Kafka, each replica of the subscriber only gets one message from a given partition key. So there's no guarantee that the agent subscribing to the WebSocket server is listening to the same partition that its message is coming out of. So we put Redis in the middle to kind of get around that.
Okay. And how do you handle multiple instances of the WebSocket server?
Sure, yeah. So when the endpoint agent first connects to the WebSocket server, it'll say, hey, I want to subscribe to my test assignments. And when it does that, the WebSocket server then subscribes to the corresponding Redis topic. So the Redis topic itself is like keyed on the agent's identifier. So only the messages for that agent are being pushed to that Redis topic. And so like once that subscription to Redis is set up, then the WebSocket server is only getting messages for the agents that it has a WebSocket connection to.
It's, by the way, great presentation. Congratulations on your first meetup. You said that in the beginning. I was just wondering more like the way the business rules of this application work. So when the test assignments get regenerated because the configuration changed, you do not provide any kind of functionality to cancel those that have been already emitted. So like they all will be pushed into the agents.
Yeah, exactly. Yeah. So the kind of like, I guess, logic that we have on the agent is that it's effectively idempotent. So if you push like the same thing twice, or like it always just holds on to the like latest state. So the actual message that we push isn't like new assignments. It's here are all the assignments that you need every single time. So it's always idempotent effectively.
Yeah, right. So there is no preference between them.
Yeah.
Thank you very much.
Could you please tell something about fault tolerance of those pipelines that you showed in the beginning, K-stream pipelines?
Like, is there a specific?
What if consumer crashes and there were messages in the middle of those pipelines?
Yeah, so the pipelines, because it's on Kafka, it's persisted. So when the application spins back up, it just kind of starts from the position before it crashed, I guess. So it like replays the message, and then we have kind of monitoring around stuff like consumer lag. So basically, how far behind is an application from the latest part of the Kafka topic? So then we get alerted for these kind of things. So like we kind of jump in manually to figure out what's wrong. Cool. Yes. Yep. Good.
All right, thank you very much. Yeah, obviously, thank you, Derek, and thank you, Juliana, as well, and thanks, TransferWise, for hosting us. We'll probably have a quick drink here, then head to the pub. Would you reckon Owl and Pussycat? Probably best. Yeah. All right, cool. Thank you very much.